Hello, welcome. Today I will talk about our joint work with Özlem, Salehi and İlknur Tepe, titled A Computer Science-Oriented Approach to Introduce Quantum Computing to a New Audience. I will go through these 4 topics very quickly. Here you can see my outline. Why we need an alternative approach or a computer science-oriented approach. What is the tool that we have used for this study, which is the Introduction to Quantum Programming workshop titled QWorld. Assessing knowledge acquisition, meaning how did we assess whether the participants actually learned something or not, and this part also includes our methods and outcomes, and a very brief discussion. So the concept of quantum awareness, or in our case quantum computing awareness, is becoming important around the world, and there are many global efforts to increase these levels of quantum awareness in general public, undergraduate students, graduate students, and industry. And 2 of the main programs are Qiskit and Q#, which are quantum programming languages introduced by IBM and Microsoft. And there are programs focused on teaching people these languages, like Qubit by Qubit or the Quantum Quest. In the bronze workshops, we use Qiskit, which is basically built upon Python. And to be able to understand these concepts, you need a basic amount of linear algebra. But that's it. In the context of quantum computing, if you want to introduce someone outside of physics, actually using the physical phenomena to explain concepts like superposition or entanglement is not really that important. So the main idea here, though, or let's say a computer science oriented approach, which is basically popularized by Scott Aronson, and it has been being used at computer science programs around the world, is that if you want to introduce someone to the concept of superposition or entanglement, you don't need to explain their physical realities in a sense. Like, you don't need to use the concept of electron spin or beam splitters and photons. You can introduce these as purely mathematical concepts or formulations. So in that sense, you bypass the requirement of quantum mechanics in quantum programming. And then after completing these elementary or introductory courses, people can go into quantum mechanics even more so prepared. So you don't need to introduce quantum mechanics first and then quantum programming, but you can introduce quantum programming as a purely mathematical construct and then introduce quantum mechanics into the mix. So this way, you actually lower the entry barrier to the field. And this was something that we tried to, let's say, demonstrate. So the QBronze workshops has been used for more than 53 workshops right now around the world in 20 countries with more than 1,800 participants who completed these workshops. And they were developed by this group of QWorld, and they aim to be as inclusive as possible, only demanding the participant to know a little bit of Python and some linear algebra concepts. And the approach that the QBronze workshops use is called a task-based approach. You introduce a concept or you do some parts, and then there are some interactive tasks that the participants should fill. This is not a new concept. This has been used to introduce programming languages for quite some time, but with the development of Jupyter notebooks, it has become increasingly available and accessible for anyone who has an internet connection and basically running computer. And to introduce this, let's say, quantum computing concepts, as I said earlier, we mainly focused on quantum programming, the circuit structure, what the circuits are in terms of mathematical sense. And to be able to encode this, we use Qiskit provided by IBM. And in this understanding, we did not try to impose the idea of quantum computing coming from quantum mechanics, but we introduced it as a natural development or natural progress of classical computing. So in classical computing, you have bits. In probabilistic computing, you have p bits, which means there are bits that can take a value between 0 and 1. And in quantum computing, you have qubits, which means that basically a mathematical entity living in Hilbert space with certain conditions. And here you can see the quote of Scott Aronson. And he says that quantum mechanics is what you would inevitably come up with if you start from probability theory and then said, let's try to generalize it. And this is actually rather useful for quantum computing as well, because quantum computing is a generalization of classical computing in terms of mathematical formalism. You don't actually need to introduce any physical route to reach quantum computing if you start from classical computation or classical computer science theories. In bronze, the workshop is basically constructed as following: classical bits, probabilistic bits, quantum bits, basics of quantum systems like the mathematical constructs of quantum states, superposition, measurement, quantum operators, controlled operators, entanglement, superdense coding, and you can see the rest. So as a measurement method, we used single group pre-post test, which means that you ask the same questions before and after the workshop, and you look at the gain of individual participants. And we were able to use this on 22 workshops. Most of them were conducted in Turkey. And the total number of participants to the workshops were 430, and the number of people who filled our pre and post tests were 370. We also gathered some other information like gender, age. None of these were mandatory, but we asked the attendance rate of the participants, and we asked some other questions like, did you have enough time? Did you enjoy the course? And stuff like that. And the knowledge test was actually rather easy. And here you can see the questions, and even one of them is actually not related to any, let's say, complicated knowledge. You just need to know that the program you're using is Python. And you can see the results here. So as you can see, there are some people who forgot what they learned, even before what they know. But most of the participants learned something, which is not surprising because, I mean, if you attend a 3-day workshop, you will definitely learn something. But what we aimed is that how the learnings were distributed. So this is for the entire workshops. The greenish parts on the below represents the distribution of previous scores, and more orange looking distributions represent the after scores. And just by looking at this, you can see that the distributions are shifted. And also, if you look at the before and after of the age groups here, so the age groups are distributed like this in terms of number. You can see that almost everyone has learned, and each age group has learned, but the good point or an interesting point for us here is that the after scores of each age group were almost identical or very similar in that sense, which means that the workshop actually does not just teach you some random stuff. It allows you to reach a certain point of knowledge. So regardless of your, let's say, previous knowledge, you reached a certain point by completing this workshop. And when you look at the gender distributions or distributions of scores with respect to gender, you can again see that, you know, previously the male participants knew more, but in the end the distribution is almost the same. I mean, only the variance is different. So you can see that the workshop actually helps you to reach a certain point, which is something that I think we should expect from an introductory level workshop by its design. And again, here you can see the distributions with respect to education level and department. And again, you can see the gain scores, the mean, and this basically shows us that as people know more earlier, if their previous knowledge is higher, they learn less. If their previous knowledge is lower, they learn more. And here you can again see this, that with respect to departments, there's not much difference between the gain scores of the participants. And we asked several questions, like what was, you know, did you receive support when you needed? Did the instructors show you interest, etc. But one of the main questions that were answered in a negative way, I mean, almost all of them are positive, but the one that got the most negative feedback was that they didn't think they had enough time to complete the tasks, which means that a 3-day workshop to introduce people into quantum computing is still a very dense workshop for at least some of the participants, because here you can see that many of the participants agreed that, you know, the timing was adequate. So the discussion section is actually rather simple. The overall significant increase in knowledge was observed. The workshops were beneficial for both male and female participants and participants with different backgrounds, meaning that different age groups, different departments, and workshops were most beneficial for high school students and participants with less pre-knowledge, meaning that if you use a computer science oriented approach and you aim to introduce people who are outside of physics to the field of quantum programming, it actually works for people who knew less in the beginning. So as the knowledge level of the participants increase, a different approach or a higher level of an introduction might be needed. But if you are aiming for the general public, the lowest entry barrier that you can impose would actually help. And this study demonstrates that. There are also similar related works that you can see and you can check. And as a conclusion, we can say that a task-based quantum programming, computer science-oriented approach is an effective method to introduce an audience with diverse background to quantum computing, which means that if you want to introduce a massive amount of people to quantum computing, probably it would be better to lower the entry barrier as low as you can. And to be able to do that, a computer science-oriented approach, which requires some Python knowledge and linear algebra, will probably outperform a workshop that, or a method that requires the participants to know quantum mechanics. And here you can see some of the references that we have used, and you can actually reach the paper via archive. It has been out for quite some time, and we would appreciate your feedbacks if you have any. Thank you, and please enjoy the rest of your conference.